Somewhere beyond Mars, 3I Atlas broke formation. It didn't tumble. It didn't drift. It steered, subtle, deliberate, and perfectly timed. Inside NASA, the anomaly appeared for less than a minute before vanishing from the public feed, replaced by static and revised coordinates. But NASA kept a copy, and the pattern they found wasn't random noise. It was control. For the first time, space itself felt aware of us. When the Asteroid Terrestrial Impact Last Alert System, or ATLAS, flagged a faint, fast-moving object that the Sun's gravity could not bind, astronomers realized they were witnessing only the third interstellar visitor ever recorded. Before it came Oumuamua in 2017 and Borisov in 2019, both of which behaved like uninvited guests passing politely through the solar system. But 3I Atlas, first detected on July 1, 2025, announced itself with an energy that felt deliberate. Its incoming velocity exceeded 42 km/s, slicing across the ecliptic at an angle no planet could have delivered. The initial orbit traced by JPL's Horizons database looked perfect, a hyperbolic path bending just enough around the Sun before accelerating back toward deep interstellar space. For months, the model held true. Observatories from Hawaii to Chile confirmed each coordinate with clock-like precision. Then, approaching mid-October, that certainty began to splinter. On October 21st at 0:12 UTC, the independent analysis collective known as Earth Exists reported that their telescope array had captured 3I Atlas several arc-minutes away from its predicted position. Their measurement placed it at right ascension 13A47M 54.3s and declination Plautus 8 degree Q 21 16.2. According to JPL's October 10th update, the object should have appeared at right ascension 13A46 Me 57.5s. The offset 1544 arc-minutes translated to roughly 1.1 million kilometers of lateral. Displacement at a distance of 2.38 astronomical units, almost 3 times the Earth-Moon span. That figure alone should have been impossible. Interstellar bodies follow gravity's script with merciless accuracy. Deviations of even a few hundred kilometers trigger re-evaluation of every observation involved. Yet 3I Atlas's range reading remained exact. There was no misidentification, no parallax misfire, no optical noise. The telescopes were locked on the correct target, but the target itself seemed to have shifted sideways in defiance of celestial mechanics. Analysts proposed software desynchronization, clock drift, and atmospheric distortion, every conventional excuse they could test. Each one failed. What remained was an object, holding perfect distance while sliding across its predicted sky track, faster than any known gravitational influence could permit. Somewhere in the cold between worlds, something had stopped following the rules. The first instinct among observers was to blame data, not physics. The 15.4 arc-minute gap, equivalent to 1.1 million kilometers at 238 AU, was simply too large for comfort. Telescopes can misalign, coordinate systems can lag, even reference stars can drift if their catalogs aren't corrected for proper motion. The Earth Exists team ran every diagnostic possible. Star fields were remapped against the Gaia DR3 reference grid. Atomic clocks were synchronized through the network time protocol. Calibration frames were recalculated with dark and bias corrections. Every check confirmed the same truth. The numbers weren't lying. The image plane was solid, the timing perfect, and yet 3I Atlas continued to sit where no software predicted it should. In orbital terms, this wasn't just a curiosity. It was a contradiction. If the observing software had relied on outdated ephemeris data from the previous quarter, the error should have leaned backward, placing the object slightly behind its projected course. That's what always happens when you use older orbital data. The object appears late because its velocity was underestimated, or a minor gravitational influence went unmodeled. But 3I Atlas didn't lag, it led. The observed coordinates showed it ahead of schedule, several minutes farther along its trajectory than Newtonian mechanics would allow. To move into that position, something had to apply force perpendicular to its orbital vector. Essentially, a push sideways through space at interstellar scales. Lateral movement of even a few kilometers per second requires staggering energy. For an icy nucleus roughly the size of a mountain, there are only 2 natural mechanisms: asymmetric outgassing or gravitational assist. Neither matched the pattern. Its spectroscopic profile showed steady water and cyanogen release, no violent jets or rotational bursts that could generate thrust, and there were no nearby bodies large enough to tug it laterally. The only variable changing was the offset itself. By late October 21st, the discrepancy was already widening at 0.23 arc-minutes, a measurable acceleration that defied the static elegance of celestial motion. The equations described a comet, but the sky displayed intent. Each pixel shift hinted that the object wasn't merely drifting through sunlight and dust, it was steering. For the first time since its discovery, the idea that 3I Atlas was under active control stopped sounding like science fiction and began to look like raw observation. In space, nothing just changes direction. Every motion, every drift, every captured orbit is the outcome of force and time, the clean math that keeps the cosmos from collapsing into chaos. But the readings from 3I Atlas began telling a story that didn't fit those rules. At first, the team thought it was a mistake, maybe a calibration slip or outdated software. Yet every test they ran said otherwise. The numbers weren't wrong. They were ahead. The comet was moving faster along its path than gravity allowed, as if it had quietly fired an invisible engine. Normally, when orbit predictions fail, scientists find a reason: a missing gravitational tug, a mistimed exposure, or an error in the model. This time nothing fit. JPL's Horizon system, updated less than 2 weeks earlier, showed a perfect trajectory. But when new observations came in on October 21st, the comet was already past the spot it was supposed to occupy. It wasn't lagging behind because of old data. It was leading, pulling away, carving through the sky on its own schedule. That single fact broke the logic of celestial motion. To gain a sideways velocity of nearly 4 km/s, an object its size would need an impossible amount of energy, the kind of impulse that only propulsion could produce. Outgassing couldn't do it. The spectral lines showed no sudden bursts of vapor or jets strong enough to push it off course. And there were no planets or asteroids close enough to bend its path with gravity. The motion was smooth, stable, and deliberate, as though some internal process was guiding it. Then came another surprise. Within the reflected light were subtle distortions, tiny flickers that hinted at organized magnetic fields. Simulations showed that pattern only forms when ionized gases are being contained, not scattered, like plasma being shaped by electromagnetic loops. If that's true, then 3I Atlas isn't just moving differently, it's managing the space around it. Comets are supposed to brighten as they approach the sun. Heat wakes the ice, jets begin to vent, and sunlight scatters through gas and dust, turning distant specks into streaks of fire. But 3I Atlas wasn't obeying that rule either. As its orbit pulled it closer, its magnitude didn't rise, it fell. The object grew steadily fainter, even though instruments confirmed it was venting more mass than before. For an object that should have been blazing brighter by the hour, the data made no sense at all. The expected reading from JPL Horizons listed its brightness at magnitude 1483, but actual measurements showed 15.11, about 26% dimmer than predicted. The difference doesn't sound large, but in astronomical terms that gap is enormous. It means the comet was reflecting only 3/4 of the light it should have. That loss couldn't be explained by distance, angle, or instrument calibration. Something was either absorbing the light or redirecting it away from Earth. That idea drew quiet attention from engineers who'd once worked on plasma containment research. They noted that the same color spectrum, green, blue, and faint pink, wasn't random noise but the signature of controlled ionization: green from cyanogen, blue from nickel ions, pink from hydrogen collisions. It looked chemical at first, until the color zones began appearing in clean geometric separations. Comets normally glow as chaotic spheres of dust and vapor, their light diffused and unshaped, but 3I Atlas was showing rings, edges, and symmetrical boundaries, as though its gases were being confined within invisible lines. It didn't resemble natural outgassing. It looked organized,